Human biological intelligence is a dense, chaotic weave of synapses and neurons. In 1957, Frank Rosenblatt attempted to replicate this messy architecture with the perceptron, the first primitive attempt at an artificial neural network. Traditional machine learning models required engineers to manually design feature extractors, hand-coding the specific rules for what the machine should look for. Deep learning automated this by passing raw data through hierarchical layers, allowing the machine to learn those features on its own. But the theory far outpaced the reality. For decades, attempts to train multi-layer architectures stalled. The hardware of the era was underpowered, and the mathematical models failed to converge, leading many researchers to dismiss the field entirely. This trajectory shifted in 2006. Researchers like Geoffrey Hinton published work on deep belief nets that allowed these multi-layered structures to train successfully, ending the period known as the AI winter. Today, deep learning drives modern industry. It is tempting to credit this growth entirely to the sudden availability of massive datasets and powerful graphics processors. But the catalyst for this expansion was a series of specific structural innovations that resolved historical bottlenecks in data representation. The most severe roadblock for early networks was the vanishing gradient problem. As a network grew deeper, the error signals used to correct mistakes during training would shrink with each successive layer, until the earliest layers simply stopped learning. The sigmoid curve was the early standard. Its tails flattened completely, causing gradients to decay to zero and freezing parameters. The fix was the rectified linear unit, or ReLU. It outputs a constant gradient for positive inputs, allowing error signals to flow backward without disappearing. Networks must navigate a massive, high-dimensional parameter space to minimize error. Standard stochastic gradient descent stepped blindly down this slope. The modern solution is the Atom optimizer. By estimating gradient moments, Atom dynamically calculates an individual adaptive learning rate for every single parameter. By solving the vanishing gradient with ReLU and stabilizing the descent with Atom, engineers established the mathematical baseline required to construct the specialized architectures that define modern AI. When early dense networks attempted to process images, they hit a structural bottleneck. They required image data to be flattened into a single one-dimensional line of pixels, which destroyed the spatial relationships that define an image. The convolutional neural network, or CNN, was engineered specifically to solve this by preserving the original dimensional structure of the data. This matrix is a raw image grid. Instead of flattening, a filter scans the grid, multiplying pixel values by its weights to capture spatial features. A pooling operation downsamples the map by extracting the maximum value from each patch, shrinking data while keeping patterns intact. Operating in sequence, the earliest layers extract rudimentary features, like contrast lines and edges. Deeper into the network, those edges are abstracted into complex geometries and recognizable shapes. By mapping space mathematically, CNNs have provided the medical field with a highly precise diagnostic tool. Modern clinical algorithms evaluate dense spatial patterns within chest X-rays and MRI scans. They detect microscopic irregularities in tumors, with accuracy matching expert radiologists. Convolutional networks dominate computer vision because their internal mathematical structure directly reflects the rules of two-dimensional physical space. While a photograph exists all at once in a static grid, speech and text unfold continuously. Processing this sequential data requires a model capable of maintaining a temporal state. Recurrent neural networks attempted to capture time by maintaining a hidden state. Each node would pass its output forward to the next step, carrying the context of previous inputs forward. However, standard recurrent networks failed on long sequences. The vanishing gradient problem returned. Over a long sentence, the initial signals decayed so rapidly that the network lost its mathematical memory of the beginning of the sequence. The architectural fix was the long short-term memory network, or LSTM. This is the LSTM cell. Instead of a simple loop, 3 gates regulate information. The forget gate evaluates previous state and new input, erasing irrelevant data. The input gate writes important sequence data into memory. The output gate calculates the precise state projected forward. LSTMs provided a mathematical mechanism to curate temporal context, enabling the development of accurate speech recognition and long-form language translation. Yet, even with curated memory, recurrent networks were constrained by time. Because data had to be processed step by step, the computation could not be executed in parallel, limiting how fast these models could train. In 2017, a breakthrough abandoned recurrence and temporal sequences entirely. The transformer model eliminated step-by-step processing, allowing massive datasets to be absorbed simultaneously. It achieved this by replacing the temporal feedback loop with a mechanism called self-attention. This matrix details self-attention. The network assigns a query and a key to every element in a sequence. Calculating their dot product generates an attention score. Those scores are applied to the values, allowing the model to instantly calculate the contextual weights of all data points simultaneously. A word at the beginning of a paragraph can mathematically influence a word at the end without having to pass through every sentence in between. This parallel processing structure is the computational engine driving modern large language models like GPT-4. By transforming time into a purely spatial mapping problem, transformers bypassed the sequence bottleneck, providing the foundation for modern generative models. These network architectures are specialized mathematical lenses. CNNs map spatial correlation. LSTMs curate temporal states. Transformers map global context across static grids. But this specialization comes at a cost. Deep learning networks are brittle. Because they are restricted by the rigid layers we've just discussed, a model trained for one task performs poorly on any new task. The next architectural frontier aims to break those limits. This is the equation for neural ordinary differential equations. Instead of passing data through stacked discrete layers, neural ODEs model the hidden states of the network as a continuous fluid trajectory. This allows the model to adaptively select its own computation steps based on the complexity of the task, mirroring the continuous physical laws of nature rather than the strict step functions of digital logic. The growth of machine intelligence is a story of structural evolution. Ultimately, the capabilities of artificial intelligence are defined by the boundaries of our mathematics.